What if the power of the largest star ever found could reshape the entire cosmos? Across the vastness of the Milky Way, in a region where interstellar dust drifts like ancient smoke and gravity sculpts the slow dance of star clusters, there exists a stellar titan whose power defies every intuition we possess about how stars are supposed to exist. It is not merely large in the way some stars are large. It is not simply luminous in the way that supergiants blaze for their brief cosmic lifetimes. Instead, this colossal furnace radiates with an intensity so overwhelming that astrophysicists struggle to fit its behavior into the mathematics that usually contain the universe. And if its power were not simply a spectacular footnote in the story of the cosmos, but a force capable of reshaping the very architecture of galaxies, then our understanding of creation, destruction, and cosmic destiny would need reconsideration from its foundations. Imagine a star so massive that its light distorts the space around it, not as a footnote of gravitational lensing, but as a luminous hammer reshaping the structure of nearby gas clouds. A star so hot that entire solar systems would evaporate into vapor before ever approaching its vicinity. A star whose gravity, magnetism, and radiation pressure are not astrophysical curiosities, but engines powerful enough to carve new pathways for cosmic evolution. What if the most gigantic star ever found was not simply one more participant in the cycle of stellar birth and death, but a force whose existence could tilt the balance of the galaxy itself? To imagine such a star, picture a sphere of incandescent plasma tens of millions of miles across, its surface boiling with nuclear reactions so extreme they resemble oceans of liquid lightning. Its interior burns at temperatures where atoms shred into subatomic chaos, and its outer layers swell and contract in cycles that release more energy in a heartbeat than our sun emits in centuries. This is a star that has surpassed the boundaries of what stellar physics comfortably explains. A star that behaves like a cosmic paradox, too massive to exist, yet somehow alive, too luminous to remain stable, yet somehow pulsing with a ferocious rhythm carved by nature's deepest laws. When astronomers first measured stars of this magnitude, they confronted a troubling reality. The theoretical upper limit for stellar mass, the so-called Eddington limit, was never meant to permit such monstrosities. Stars above a certain mass should, by all logic, blow themselves apart in violent eruptions long before they can grow into titans. Their own radiation should tear away their outer layers faster than gravity can hold them together. Yet here stands the largest star ever found, a beacon shattering the assumptions built into entire branches of astrophysics. It forces us to ask, what allows such a star to exist at all? And if it exists, what could its power mean for the galaxy surrounding it? The power of such a star begins with its light. Light is often treated as a passive messenger, a stream of photons carrying information across the void. But from a star of this magnitude, light becomes a force, a pressure, a wind. It becomes a sculptor capable of chiseling vast nebulae into new shapes, pushing matter across parsecs, compressing gas clouds into knots that collapse into new stars. Radiation from such a titan doesn't simply illuminate its stellar nursery, it dominates it, rewrites it, accelerates processes that would normally take millions of years into spans so brief that the surrounding region becomes a laboratory of cosmic fast-forward. Now imagine that same radiation interacting with the dark filaments of molecular clouds drifting nearby. Under ordinary circumstances, these clouds collapse under their own gravity, forming clusters of stars across millions of years. But under the assault of a hyperluminous giant, the pressure of photons becomes a trigger. Clumps compress rapidly, temperatures spike, the equilibrium that keeps protostars in suspended animation collapses. Entire star clusters ignite into existence at once, not slowly, not patiently, but as though commanded into being by the presence of a stellar emperor. This kind of star does not simply exist in its region of space, it governs it. Even gravity cedes authority to the blazing force of its radiation. Ordinarily, gravity shapes the structure of galaxies. It binds matter into spirals, tethers stars to their orbits, and forms halos of dark matter that extend far beyond the light we see. But near a star of unprecedented mass, radiation competes with gravity on scales unheard of. The outward pressure becomes so intense that dust grains, molecules, and even ionized gas no longer drift passively. They are flung outward in luminous streams. The star becomes a hurricane at the center of its domain, a cosmic cyclone reshaping the distribution of matter for dozens of light years in every direction. But the power of the largest star ever found is not limited to shaping the immediate clouds around it. Its influence extends into realms where its magnetic fields, particle winds, and intense ultraviolet radiation begin to disturb entire regions of interstellar medium. Charged particles accelerate into relativistic jets. Shockwaves propagate outward into the ambient gas. The ultraviolet light strips electrons from atoms across vast distances, altering the ionization balance of gas that will one day form future systems. If such a star lies near the spiral arms of a galaxy, its effects ripple outward like seismic tremors. The density waves that form spiral structures, those grand sweeping arms, are sensitive to variations in mass distribution and energy injection. A star this massive could cause a localized distortion in the arm, thickening it, enriching it, or fracturing sections of it into smaller star-forming pockets. In extreme scenarios, the birth or death of such a colossal star could reshape an entire segment of the spiral arm, leaving behind structures that persist for billions of years. Now consider the role of gravity itself. A star this massive carves a gravitational well so deep that nearby stars feel its tug. It subtly alters their orbits, pulling them into elongated paths, disrupting star clusters, and shifting the harmony of entire stellar neighborhoods. Gravity is an artist that works slowly, but a star of unprecedented mass provides the brushstrokes that leave permanent imprints on the canvas of the galaxy. Its magnetic fields add yet another layer of influence. Magnetic fields around massive stars are dynamo engines that trap charged particles, launch stellar winds, and shape vast magnetospheres. For the largest star ever found, these fields can stretch for dozens of astronomical units, carving cavities in the interstellar medium and accelerating cosmic rays that journey across the galaxy. Cosmic rays from such titans may even influence planetary atmospheres thousands of light years away, altering climate cycles on worlds that will never know the source of their invisible bombardment. But these are only the influences of the star while it is alive. The most profound transformation comes at the end, because a star of unimaginable mass does not die quietly. It does not fade gently like small stars. It dies violently, catastrophically, gloriously, through a process that can send shockwaves rolling across the arms of its galaxy. When such a star collapses, the explosion is not large in any conventional sense. It is not merely a supernova. It may reach the level of a hypernova, an explosion so powerful that a single moment releases more energy than billions of stars combined. It may produce gamma-ray bursts, narrow jets of radiation so destructive that if one were pointed at Earth from thousands of light years away, it could erase our atmosphere in moments. But beyond the destruction lies creation. The shockwave from such a colossal explosion sweeps through the region, compressing gas, triggering star formation on enormous scales. Heavy elements forged in the star's core, elements essential to planets, biospheres, and life, are scattered across hundreds of light years. The death of a giant seeds a galaxy. Planets that will form billions of years later carry within them the ashes of the titan that once reigned above them. Now imagine this power not as a singular event, but as a repeating cosmic mechanism. Imagine a galaxy with dozens of such stars. Imagine an early universe where conditions were ripe for producing giants far larger than any star today. Their lives would have shaped the galaxies we now observe, carving them, igniting them, enriching them, bending them into the structures we recognize across the night sky. What if the largest star ever found was not just a marvel, but a clue? Evidence that stellar titans once exerted far more influence over the architecture of the cosmos than we realize. What if their combined power sculpted galaxies into spirals, forged stellar highways, and dictated where planets could form? If the cosmos was shaped by such giants, then every atom of iron in your blood, every molecule of calcium in your bones, every grain of dust beneath your feet carries the heritage of stars. So massive that their existence defies our equations. We are shaped by their power. Our galaxy is shaped by their power. The universe itself may bear the fingerprints of stellar titans whose deaths rewrote the laws of cosmic structure. Far beyond the luminous crown of the largest star ever discovered, its influence continues to ripple through the cosmic fabric in ways both subtle and cataclysmic, extending its reach into realms where matter is delicate, diffuse, and vulnerable to the slightest perturbation. Such a star is not simply a beacon in the night, but an engine powerful enough to alter the developmental trajectory of entire celestial neighborhoods. To understand the magnitude of this influence, we must step into the blackened corridors of molecular clouds, the quiet nurseries of the cosmos, where faint glimmers of starlight struggle to penetrate thick curtains of interstellar dust. There, in those dark, frigid expanses, gravity works slowly and silently, coaxing wisps of gas into denser pockets, sowing the seeds of future suns. Yet the presence of a hypermassive star introduces a violent tempo into this gentle cosmic process. Instead of awaiting the slow rhythm of collapse, the immense radiation pressure from the giant acts like a sculptor wielding a chisel forged from pure energy. Its photons crash into gas clouds with ferocity, stripping electrons, ionizing atoms, and forcing shock fronts through the medium. These shock fronts become cosmic detonators, triggering bursts of star formation with an urgency that disrupts the ordinarily patient cadence of stellar birth. But the influence is not uniform. It is directional, chaotic, and deeply dependent on the structure of surrounding gas. Where the gas is dense, the radiation compresses it further. Where the gas is sparse, it is eroded away entirely. The result is a cavernous, bubble-like structure surrounding the star, often spanning dozens or even hundreds of light years. Within this cavity, star formation becomes a controlled burn, sudden, intense, and short-lived. Outside of it, the vacuum grows as gas is pushed outward, reshaping the surrounding terrain like a cosmic wildfire. This phenomenon is not unique to large stars, but the magnitudes involved for the largest star ever found are incomparable. Astronomers have observed these cavities before, ionized regions called H2 regions, but those pale in comparison to the structures carved by a star whose luminosity is millions or even tens of millions of times greater than our sun's. It is as if the star has replaced the typical gentle breath of starlight with a hurricane composed entirely of photons. Yet even this is only the beginning. Beyond light and radiation pressure lies another domain of influence, the gravitational footprint of such a star. Though its mass is enormous, it is not merely the number of atoms that matters, but the gravitational gradients it imposes on its surroundings. Any smaller stars that form nearby will feel their orbits subtly twisted. Planetary systems that might attempt to coalesce in the vicinity would be stretched, destabilized, or torn apart entirely. Dust disks around young stars could tilt, warp, or scatter under the influence of gravity that is too powerful to ignore. But then comes a deeper question. Could a star of unprecedented magnitude reshape the behavior of an entire galaxy? To answer this, we must dive into the realm of stellar feedback, one of the most significant but least intuitive mechanisms governing cosmic evolution. Stellar feedback refers to the energy poured back into the interstellar medium by stars. For ordinary stars, this includes stellar winds, ionizing radiation, and eventual supernova explosions. For hypermassive stars, these processes occur at such colossal magnitudes that their combined effect can become a dominant driver of galactic structure. Consider the spiral arms of galaxies, those graceful, sweeping arcs composed of billions of stars. Their form is defined by density waves, patterns where matter compresses as it passes through. Hyperluminous stars within these arms act like accelerants. Their radiation increases the pressure in local regions, influencing how the density wave propagates. If enough of them cluster together, they could reshape the spacing between arms, thicken certain regions, distort others, even create breaks or forks within the structure. They could turn a clean spiral into a warped, chaotic pattern that retains the memory of their violent presence long after they are gone. Now imagine a region dominated not just by one, but by a group of such massive stars forming nearly simultaneously, an event that becomes possible in the densest star-forming clusters where gravity funnels absurd amounts of gas into compact volumes. Their combined radiative power would create overlapping shockwaves, colliding cavities, and expanding shells of ionized gas. These interactions could birth new stars in an accelerating cascade, or they could strip entire regions clean, leaving behind vast pockets of emptiness. In both cases, the galaxy's evolution would be rerouted, sculpted by the explosive influence of these stellar monarchs. Then there is the overlooked but essential mechanism of stellar winds. Stars of extraordinary mass do not merely emit light, they shed matter at rates that can only be described as violent. Their stellar winds carry away billions of tons of material every second, blasting outward at thousands of kilometers per second. These winds stir the interstellar medium like a cosmic blender, enriching it with heavy elements, mixing it, heating it, and sometimes clearing it entirely. For the largest star ever found, the winds may carry enough mass each year to equal several Earths, or even entire planets. Over the star's lifetime, these winds could expel material equivalent to dozens of solar masses, meaning the star loses a significant fraction of itself before it ever reaches the point of terminal collapse. This lost material does not drift harmlessly into space. It seeds the galaxy with carbon, nitrogen, oxygen, and the heavier elements that form planets, atmospheres, and eventually the chemistry of life itself. The galaxy becomes richer, more diverse, more capable of forming complex systems. This enrichment is not random. It is directed by the physics of the star, by where its winds collide, where its radiation pushes matter, and where its gravitational influence binds or disrupts structures. The largest star ever found thus becomes a cosmic fertilizer, a star whose mere existence accelerates the chemical evolution of a galaxy. Without such stars, galaxies would be poorer, duller, slower to develop rocky planets or biological potential. Their influence extends far beyond their brief lifetimes, shaping the potential for life long after their own brilliance has faded. But to appreciate the full scope of such influence, we must consider the ultimate fate of this behemoth. Stars of extreme mass do not end their lives gently, nor do they produce ordinary supernova. Instead, they may undergo a type of collapse so catastrophic that it dwarfs the fury of any supernova humanity has ever witnessed. These are hypernovae, events that pour more energy into the surrounding space in seconds than the sun will emit over its entire 10 billion year lifetime. The shockwave from such an explosion is not simply destructive, it is transformational. As it races outward, it compresses gas clouds, triggers secondary star formation, enriches regions with newly forged heavy elements, and resets the evolutionary clock of entire stellar neighborhoods. Where once there was calm, there is now chaos. Entire clusters might be disrupted. Systems of young stars might be hurled from their cradles. New gravitational gradients emerge as material is redistributed on scales spanning dozens of light years. At the core of the collapse, something far stranger occurs. For stars above a certain mass threshold, the collapse is so complete, so violent, that the resulting remnant is not a neutron star, nor even a typical black hole. It may be a black hole of intermediate mass, a rarity in the universe and a key puzzle in modern astrophysics. Such a black hole would not simply sit as a quiet remnant. It would feed aggressively, pulling in whatever material remains nearby. Its accretion disk could glow with X-rays brighter than entire galaxies. Jets of material moving at near-light speeds could burst outward, punching holes through the interstellar medium and creating tunnels of ionized gas that persist for millions of years. If aligned toward us, those jets could produce gamma-ray bursts, beams of energy so intense they defy comprehension. A gamma-ray burst directed at a distant world could sterilize it completely. A burst passing through the galaxy could alter molecular chemistry in gas clouds thousands of light years away, changing the pathways through which future stars and planets form. Thus, the death of a hypermassive star may not simply be an ending. It may be a cosmic wound that takes epochs to heal. But the influence does not end there. The black hole left behind becomes a gravitational anchor, pulling stars into orbit, reshaping the trajectories of clusters, and bending the paths of matter in ways that ripple through the galaxy for eons. If multiple such black holes form in close proximity, their interactions could produce gravitational waves, subtle ripples in the fabric of space-time that travel across billions of light years, carrying with them the echo of the star's ancient demise. In the early universe, these stars may have been common. They may have shaped the large-scale distribution of galaxies, influenced the formation of galaxy clusters, and seeded the earliest black holes that later grew into the supermassive black holes anchoring modern galaxies. Their power may have been a fundamental driver of cosmic evolution, in an era long before the Milky Way existed. In that sense, the largest star ever found may not be an anomaly. It may be a survivor, a relic from an age when the universe was younger, denser, and richer in the gas clouds necessary to form such beasts. Observing it today is like glimpsing a primordial blueprint, a reminder of the forces that once dominated the cosmos before time thinned the interstellar medium and star formation became gentler and more predictable. Yet the greatest mystery remains not merely what these stars are, but what they imply. If a star can alter the fate of a galaxy, what does that say about our place in the cosmic story? What does it say about the origins of life, the structure of the cosmos, and the delicate balance of forces that shaped everything we see when we look up at the night sky? The question becomes unavoidable. Are we living in a universe shaped not by quiet processes of gradual evolution, but by the violent reign of stellar giants whose power rewrote the rules of creation itself? The power of the largest star ever found does more than bend space, ignite worlds, and generate cosmic hurricanes of plasma. Its influence begins long before it reaches maturity, long before its surface balloons into a swollen red sphere capable of swallowing entire orbits. To understand how such a monster might reshape the entire cosmos, we must return to a time when it was not yet a star at all, when it was still nothing more than a knot of collapsing gas inside a cold, silent molecular cloud. Because even in its infancy, long before fusion begins, a future titan already distorts the universe around it. In the dark regions where stars form, gravity works at a slow, relentless pace. Molecular clouds stretch for hundreds of light years, filled with dust grains and frozen particles drifting in temperatures colder than the surface of Pluto. Yet hidden inside these clouds are pockets where material begins to clump together. As these clumps grow, their gravity strengthens. The largest star ever found likely began in such a cradle, but unlike ordinary stars, it formed from an unusually massive reservoir of hydrogen, a portion of the cloud so dense and so large that it contained the raw material for dozens of suns. As gravity pulled this material inward, the collapsing protostar heated rapidly. Fragmentation, the process by which most clouds split into multiple smaller stars, did not occur. Instead, all the mass plunged into a single gravitational well. This prevented siblings from forming and allowed nearly all available material to funnel toward one central object. A normal star is limited by radiation pressure during formation. The heat generated by the growing core pushes back on incoming material, stopping further growth. But this future behemoth found a way around that limit. Its accretion disk funneled gas into the star so quickly that radiation had no time to push it away. Jets of material blasted from its poles, but most of the mass still flowed inward. It grew not linearly, but explosively, feeding on the cloud like a cosmic vortex. Within a few 100,000 years, it surpassed dozens, then hundreds of solar masses. Even at this stage, it was already reshaping its surroundings. Radiation from the protostar ionized nearby gas, carving out a glowing bubble within the molecular cloud. Shock waves pushed against the surrounding material, compressing some regions and dispersing others. What would later become thousands of future stars emerged because of these early disruptions. The giant star's formation triggered starbirth across the entire cloud, a single object reorganizing a region dozens of light years across. When fusion finally ignited in its core, the transformation was instantaneous. Temperatures soared to millions of degrees. Photons burst outward in waves of blinding radiation. Stellar winds tore through the surrounding cloud with the force of billions of H-bombs running non-stop. The star announced its arrival not with a whisper, but with a detonation of light that illuminated an entire region of space. For thousands of years, it served as a beacon visible even through thick veils of dust, its extreme luminosity pouring energy into the surrounding environment. But for a star of this size, energy release is not simply illumination, it is domination. The surrounding regions bent to its will. Dust evaporated, molecules disintegrated. Young stars forming nearby were stripped of their planetary disks, preventing entire solar systems from ever emerging. Even during its early life, it sterilized its surroundings so thoroughly that any planets that might have formed within dozens of light years would have been bathed in lethal ultraviolet radiation. Life never had a chance in this region of the galaxy. The The giant star claimed the territory as its own. The structure of space itself began to warp around the star. Gravity is not merely a force, but a curvature of spacetime, and a star so massive creates a profound dent in the cosmic fabric. Nearby objects shifted subtly in their orbits. Photon paths bent as they traveled near the star. Over thousands of years, these distortions reshaped the motion of entire clusters, altering stellar trajectories in ways that would ripple outward for millions of years. A star like this does not simply exist, it orchestrates, and as it settled into main sequence life, a new type of influence emerged. When a massive star fuses hydrogen into helium, it produces extreme amounts of radiation, but as its temperature rises, it crosses into territory where photons become not just bright, but destructive. Gamma rays burst from its surface. Ultraviolet light strips electrons from atoms. Stellar winds blast millions of miles outward, scooping up gas and dust with unimaginable force. These winds can sweep away entire nebulae, shaping them into arcs and pillars that remain visible long after the star dies. In the most massive stars, fusion reactions occur so quickly that the star begins producing heavy elements in just a few million years. This giant forged carbon, oxygen, and neon at a pace that dwarfed anything seen in ordinary stellar lifetimes. It pushed into advanced burning cycles at an unprecedented rate. With each new fusion layer, the star became more unstable, generating convective currents capable of launching colossal eruptions from its surface. Observatories detecting such stars have found that their outer layers move chaotically, as if the star itself were boiling from the inside out. Eruptions from the largest stars can eject more mass in a single outburst than the Sun loses in an entire million-year period. The shockwaves from these eruptions travel for light years, compressing interstellar matter and igniting new rounds of star formation. The star becomes not only a destroyer, but a creator, a sculptor of nebulae, a generator of new suns, a cosmic architect. Yet these processes pale compared to the mad rush that begins once the star approaches the limits of its stability. As it burns its way through heavier and heavier elements, its core races toward the ultimate dead end, iron. Fusion builds each successive layer in increasingly frantic timescales. Carbon burning lasts hundreds of thousands of years. Neon burning lasts a year. Oxygen burning lasts months. Silicon burning lasts mere days. And then, silence. For the most massive star ever discovered, this moment is not simply a collapse. It is a cosmic event capable of shaking the galaxy. When gravity finally overwhelms the outward pressure of fusion, the core collapses at a significant fraction of the speed of light. Protons and electrons slam together, forming neutrons and releasing a flood of neutrinos so intense that for a brief moment, the star shines brighter in neutrinos than in photons. But the outer layers do not yet know the core has collapsed. They continue falling inward, racing toward a core that no longer exists as normal matter. When this infalling material strikes the dense core, a shockwave forms, traveling outward with more energy than our Sun will ever emit in its entire 10 billion year lifetime. Under normal circumstances, this shock would produce a supernova visible from thousands of light years away. But the largest stars do not settle for normal circumstances. They surpass thresholds that lead not to ordinary collapse, but to catastrophic failure of the core's internal structure. In a star truly beyond the limit of known physics, temperatures in the core can become so extreme that photons convert into electron-positron pairs, reducing radiation pressure and triggering a runaway implosion. The collapse accelerates beyond anything observed in ordinary supernovae. What follows is not merely an explosion, it is annihilation. In a pair instability collapse, the star tears itself apart in a detonation so powerful it unbinds the entire object, leaving no remnant behind. But if the star is even more massive, the collapse may bypass this destructive outcome entirely, plunging the core directly into a black hole before the explosion can unfold. In such a scenario, all of the energy, all of the mass, all of the momentum becomes trapped in a spinning gravitational singularity, but the surrounding layers continue falling, forming a dense accretion disk around the newborn black hole. This disk becomes an engine, a machine capable of generating the most powerful astrophysical phenomenon in the universe. Angular momentum channels matter into narrow beams that fire outward from the poles at nearly the speed of light. These beams, called relativistic jets, pierce through the surrounding layers like cosmic drills. If the jets break free, they unleash the type of event astronomers call a hypernova, an explosion so bright it can outshine an entire galaxy for months. If one of these jets were aimed at Earth, it could sterilize the planet from thousands of light years away. Luckily, the largest star ever found lives far beyond this lethal radius, but its hypernova would still be visible from Earth as a bright new star, bright enough to cast shadows at night and rival the glow of Venus in the morning sky. The explosion hurls heavy elements into the galaxy at incredible speeds. Gold, platinum, uranium, all forged in the final, violent moments, scatter through space, enriching nebulae and seeding future star systems. Over millions of years, these elements may become part of new planets, new oceans, new forms of life. The star's death becomes a gift to the cosmos. But what truly reshapes the universe is what remains after the explosion. A black hole of astonishing mass lingers as the final artifact of a life lived on cosmic extremes. Over time, this black hole may pull in nearby stars, gas clouds, and rogue planets. It may drift across star clusters, altering orbits and destabilizing systems. If it merges with another black hole, an event astronomers now know occurs regularly across the universe, the resulting collision could release gravitational waves powerful enough to ripple across hundreds of millions of light years. And so the star's influence continues long after its light fades. From its formation to its explosion to the final gravitational echo of its death, a single star shapes entire regions of space. It ignites worlds, erases others, sculpts nebulae, seeds galaxies, and leaves behind a remnant capable of tearing stars apart like paper. This is the true power of the largest star ever found. It does not merely shine, it rearranges the universe. The power of the largest star ever found does not end with its birth, nor with its catastrophic death. Its influence expands far beyond the boundaries of a single stellar lifetime, reaching across cosmic scales in ways that challenge our understanding of how the universe structures itself. To explore the true scope of its power, we must follow the consequences of its existence outward, into the turbulence of interstellar space, the architecture of spiral galaxies, and even the subtle shaping of the cosmos on scales so vast that no telescope can ever fully capture them. Long after the star has carved bubbles of ionized gas into its natal cloud and ignited chains of star formation across dozens of light years, its radiation continues to ripple through the galaxy. Photons emitted from its surface are not passive travelers. They are agents of change, charged with energy that transforms everything they encounter. Ultraviolet radiation strips electrons from atoms, turning cold hydrogen into glowing plasma. Infrared waves heat dust grains, causing them to re-emit light that reshapes the thermal balance of entire nebulae. Even the pressure of starlight, the gentle push of radiation, can slowly move interstellar particles over millions of years. For a star of unprecedented luminosity, this pressure is not gentle, it is relentless. Dust clouds exposed to the giant's light are blasted outward, eroding into structures of towering pillars and sweeping arcs. These shapes, carved by radiation and sculpted by winds moving at millions of miles per hour, become iconic features of the galaxy, vast sculptures that can stretch for light years. Some of the most beautiful nebulae ever observed are built by the violent artistry of such stars. Inside these illuminated clouds, something unexpected happens. While the outer layers are stripped away, the compressed regions inside collapse into new stars. This paradox, destruction creating creation, is one of the defining patterns of the universe. One massive star, through sheer intensity, can serve as the catalyst for entire clusters of smaller stars. And so even before its death, the largest star contributes to galactic evolution by shaping the next generation of suns. But its influence reaches far beyond its immediate neighborhood. In spiral galaxies like the Milky Way, the distribution of mass is profoundly influenced by stellar feedback, the combined effect of radiation, winds, and supernova explosions. Ordinary stars create turbulence in the interstellar medium. A hypermassive star generates chaos on a different scale entirely. Its winds carve out cavities that can grow to dozens of light years across. These cavities are not empty. They fill with superheated gas tens of millions of degrees hot, expanding outward and pushing against denser regions of the galaxy. When multiple giant stars form in the same region, their combined winds merge into colossal superbubbles. structures so large they pierce through the galactic disk and vent hot gas into the halo. The largest star ever discovered would inevitably have participated in such interactions, helping to launch fountains of plasma high above the plane of the galaxy. Over millions of years, these fountains rain back down as cooler gas, enriching the galaxy's chemistry and influencing star formation cycles on timescales longer than human civilization has existed. Thus, even before the star's dramatic ending, its presence subtly reorganizes the galaxy's internal flow of matter. But when the star finally reaches the terminus of its evolutionary path, its influence shifts into a new mode, one governed not by light, but by shock. A hypermassive star's death is not merely an explosion, it is a restructuring of space. The shockwave that bursts outward from the core carries unimaginable energy. For ordinary stars, this shock might influence regions tens or hundreds of light years away. But for the largest star ever found, the radius of influence could extend for several hundred light years, sweeping through the interstellar medium like a cosmic tsunami. Every molecule in its path is subjected to extremes of temperature and pressure. Gas clouds that once drifted silently are compressed into star-forming knots. Some clouds collapse almost instantly, igniting new stars within centuries, a blink in cosmic time. Others are shredded, their potential snuffed out before planets or systems could form. This is the duality of the giant's demise, the power to create on one side of the shock and the power to erase on the other. The star's heavy element ejecta travel vast distances. Carbon, nitrogen, oxygen, silicon, each atom forged in the furnace of the giant and launched into the galaxy will one day settle into new cosmic structures. These atoms join diffuse gas clouds, drifting for millions of years until gravity draws them into the next generation of stars. Over billions of years, they will become parts of planets, continents, oceans, atmospheres, and perhaps even living organisms. A single star, one colossal engine burning across the cosmos, becomes the ancestor of countless future worlds. But even this is only the beginning of the story. The most dramatic influence on the cosmos comes not from the shockwave, not from the radiation, not from the winds, but from the remnant left behind when the light goes out. Whether the star ends in a pair instability explosion that leaves no remnant or collapses into a black hole of staggering mass, either outcome bends the universe around it. If the star leaves behind a black hole, its influence stretches far across the galaxy. Black holes warp spacetime so powerfully that they alter the movement of stars thousands of light years away. Though their gravity weakens with distance, their presence can reshape orbits in nearby clusters, destabilize binary systems, and trigger the migration of gas clouds. If the black hole captures a companion star, either one formed nearby or a younger star that drifts too close, the system becomes a dramatic source of high-energy radiation. As the companion's material spirals in, it heats to millions of degrees, forming an accretion disk, visible from across the galaxy in X-rays. Jets of plasma erupt from the poles of the black hole, traveling at nearly the speed of light and stretching for light years into space. These jets plow through interstellar gas, creating bubbles of high-energy radiation that carve tunnels into the galaxy. And then there is the possibility, frightening, awe-inspiring, and profoundly consequential, that the black hole may one day collide with another. Black hole mergers are not rare on cosmic timescales. If the remnant of the largest star ever found drifts through a dense star cluster, it may encounter another massive black hole. When their orbits decay and they finally spiral together, the resulting merger would release more energy in gravitational waves than all the stars in the universe emit in light during the same moment. These ripples move outward at the speed of light, subtly stretching and compressing the fabric of the universe. They pass through stars, planets, and even living beings without resistance. They are whispers of a cosmic event so violent that the geometry of reality itself responds. But the influence of such a star is not limited to the gravitational echoes of its death. In some cases, stars of extreme mass can shape the evolution of entire galaxies. Consider regions where hypermassive stars form in clusters, compact groups of dozens or even hundreds of such titans. Their combined winds, radiation, and supernova explosions can sweep out the central regions of dwarf galaxies, blowing away the gas needed for future star formation. In this way, massive stars may control the growth of galaxies, limiting their ability to produce new stars. In larger galaxies, clusters of hypermassive stars can drive starburst cycles, periods where the galaxy forms stars at incredible rates, followed by long, quiet intervals. The energy these giants inject into the interstellar medium determines when gas collapses into new stars and when it remains too hot and turbulent to settle. The entire life cycle of a galaxy can be dictated by just a few exceptionally massive stars. Some theories even propose that the earliest supermassive black holes, those found at the centers of galaxies, may have originated from the collapse of stars, not unlike the largest star ever discovered. In the early universe, conditions may have allowed stars of enormous mass to form directly from primordial gas. These giants collapsed into black holes, weighing tens of thousands of suns, which then grew over billions of years into the titanic monsters at the centers of galaxies today. If this scenario is correct, then the largest stars are not merely influential, they are foundational. They are the seeds from which cosmic structures grow. Galaxies may owe their shape, their behavior, and even their continued existence to these massive stellar ancestors. The entire architecture of the universe, from spiral arms to galactic clusters, may trace its lineage back to colossal stars whose lifetimes lasted only a few million years. Even the expansion of the universe may carry faint imprints of these stars. Supernovae from hypermassive stars contribute to the background of high-energy particles drifting through intergalactic space. These particles interact with magnetic fields, dark matter, and cosmic filaments in ways that subtly influence the behavior of the large-scale structure of the cosmos. While these effects are small, they are cumulative. Over billions of years, the influence of hypermassive stars may help shape how matter clumps together on cosmic scales. In this way, a single star, born in a forgotten corner of a galaxy, can affect the universe long after its light has vanished. Its influence echoes through chemical enrichment, galactic evolution, black hole formation, gravitational waves, and the structure of cosmic filaments. Its life is brief, but its legacy lasts longer than galaxies themselves. This is the power of the largest star ever found, not the brightness of its surface, nor the violence of its death, but the permanence of its influence. It reshapes space, time, matter, energy, and the very future of the cosmos. The largest star ever found does not merely shape its galaxy through light, shock, and gravity. It reshapes the very architecture of matter itself. Its influence extends deep into the microcosm, into the atomic heart of the universe where protons and neutrons bind together to create the fabric of reality. The power of such a star does not end at radiation or destruction. It forges the fundamental components of future worlds, rewriting what can and cannot exist in the cosmos. To understand the full scope of its power, we must dive into the nuclear furnace at its core and follow the journey of matter from simple hydrogen atoms to the heavy, complex elements that make planets possible. Inside the core of a star so massive, the pressures are beyond anything that can be recreated in any laboratory on Earth. At the heart of this celestial monster, hydrogen nuclei collide at velocities so extreme that quantum barriers dissolve. The star's internal temperature reaches hundreds of millions of degrees. Under these conditions, matter behaves not like the calm, orderly structure familiar to us on Earth, but like a seething ocean of charged particles, swirling in a state of perpetual violence. Hydrogen fuses into helium with staggering efficiency, releasing energy that spills outward in torrents of radiation. For the largest stars, however, this initial stage lasts only a fraction of their brief lifetimes. They burn through their hydrogen supply millions of times faster than ordinary stars. In a few million years, a cosmic blink, the core becomes dominated by helium, and the star shifts into the next stage of nuclear evolution. Helium fusion requires even greater pressures and temperatures. In the core, 3 helium nuclei merge to form carbon in a process known as the triple alpha reaction. For most stars, this phase is intense but manageable. For the largest stars, it unleashes a chain of reactions that proceeds at accelerating speed. As carbon accumulates, some helium nuclei fuse with it to produce oxygen. Then carbon itself fuses into neon and magnesium. As if racing against its own gravitational collapse, the star burns heavier elements in a frantic attempt to maintain equilibrium. Each new fusion stage adds another layer to the star's internal structure. The core becomes a nested sphere of burning shells, hydrogen on the outside, then helium, then carbon, then oxygen, then neon, and finally silicon. It resembles an onion the size of a solar system, glowing with unimaginable fury, each layer a nuclear foundry producing the next critical building block of cosmic chemistry. This layered structure is not just a physical arrangement, it is a cosmic factory. Within these layers, all the elements necessary for life are forged. Without massive stars like this one, the universe would contain almost nothing but hydrogen and helium, too simple to form rocky planets, too limited to allow complex chemistry, too barren to host life. In the hearts of these stars, carbon bonds form, silicon lattices emerge, and oxygen nuclei take shape. Every breath we take, every cell in our bodies, every grain of sand on every beach in the universe owes its existence to the thermonuclear fury inside stars of this magnitude. But the nuclear furnace has limits. When silicon burning begins, the core enters its final stage of life. Silicon fuses into iron through a series of rapid reactions that generate increasingly dense nuclei. Iron is unique in the universe. It is the endpoint of stellar fusion. Creating heavier elements from iron requires more energy than it produces. Once the core becomes iron-rich, fusion halts. The star has reached its physical limit. Nothing can prevent what comes next. As the fusion-generated pressure that once held gravity at bay disappears, the core collapses at a staggering fraction of the speed of light. In less than a second, the core compresses to a density so high that it challenges the limits of physics. Electrons and protons combine to form neutrons, releasing a flood of neutrinos. These ghost-like particles stream outward through the collapsing core, carrying away energy faster than any known process in the universe. Under normal circumstances, this collapse would trigger a supernova, a violent explosion that tears the star apart and scatters its heavy elements into the galaxy. But for the largest stars, the collapse becomes something even stranger. The core's immense mass pushes neutron degeneracy pressure beyond its breaking point. Even neutrons, the densest known form of stable matter, cannot withstand the gravitational weight. When this threshold is crossed, the core becomes a black hole. The outward moving shock stalls, then reignites as the outer layers slam into the newly formed singularity's surrounding disk. This moment, where matter transitions from physical reality into space-time distortion, is where the largest stars reveal their true power. The collapse releases an energy so vast that it can outshine galaxies. The shock front that tears through the star's atmosphere can accelerate matter to relativistic speeds. And behind the veil of the event horizon, the singularity forms, a region where space folds in on itself and time slows to an eternal standstill. But even this catastrophic ending does not mark the limits of the star's influence. For a brief period after its collapse, the black hole formed from the star's core becomes a cosmic engine. The material spiraling into it heats to billions of degrees, forming an accretion disk alive with magnetic turbulence. These magnetic fields twist and amplify, channeling energy into narrow jets that erupt from the black hole's poles at nearly the speed of light. These jets are among the most destructive forces in the universe. They blast through the dying star's outer layers, sweep through surrounding regions of space, and can carry enough power to ionize matter thousands of light years away. A single such jet, properly aligned, could sterilize entire star systems, stripping atmospheres from planets and dismantling fragile organic molecules. Fortunately, the most massive known star lies far from Earth, but the mere existence of such cosmic artillery challenges our understanding of how life survives in the universe at all. Yet, destruction is only one aspect of this transformation. As the shockwaves from the star's death ripple outward, they collide with cold clouds of gas and dust in the galaxy. These clouds compress under the shock's pressure, and new stars ignite inside them. The heavy elements carried by the ejected material mix into the clouds, enriching them with ingredients needed to form planets and, potentially, living organisms. Every rocky world owes its existence to the remains of stars like this one. This cycle, birth, evolution, death, and rebirth, unfolds across billions of years. Each generation of stars enriches the universe with more heavy elements, enabling the formation of increasingly complex structures. Giant stars accelerate this cycle dramatically. In just a few million years, a single hypermassive star can transform a barren region of the galaxy into one filled with newborn stars and newly enriched gas. In this way, it acts as a cosmic catalyst, speeding the evolution of galaxies and shaping the environments in which planets and life can emerge. Perhaps the most profound influence of these stars rests in how they affect the evolution of cosmic structure on the largest scales. In the early universe, the first stars may have been even more massive than the largest known stars today. Their supernovae blasted heavy elements into the cosmos for the very first time. Their remnants may have collapsed into the seeds of the supermassive black holes that now inhabit the centers of galaxies. Without these ancient giants, galaxies may never have grown to the sizes we see today. Spiral arms, star clusters, and globular galaxies. Their existence may trace back to the first supermassive stars that shaped the universe at the beginning of time. This connection between the largest stars and the formation of supermassive black holes opens a window into an even larger influence. These gigantic black holes, weighing millions or even billions of solar masses, become engines that shape entire galaxies. Their gravitational pull organizes orbits, their jets sculpt galaxy clusters, and their accretion disks emit radiation that can influence regions hundreds of thousands of light years away. If the largest known stars represent the birthplace of these black hole seeds, then their impact reaches to the very edges of the universe. Every galaxy, every cluster, every large-scale filament of matter may have been shaped indirectly by the explosive deaths of hypermassive stars. They serve as the architects of cosmic structure, yet even this does not fully encompass their influence. On the smallest scales, within the spaces we can touch and breathe, their fingerprints remain. Every oxygen atom in our bloodstream was forged in stellar furnaces. Every calcium atom in our bones, every carbon atom in our DNA, every iron atom in our blood. These came not from planets, not from Earth, but from stars like the largest one ever found. When such a star dies, it is not an ending. It is the beginning of something new. Its atoms travel through the galaxy. They drift through interstellar space for millions of years. They become part of new stars, comets, meteors, and planets. They crystallize into rocks. They dissolve into oceans. They form biomolecules. They breathe. They think. They wonder. The largest star ever found may be unimaginably distant, but its power is not confined to astronomical charts. Its power is here, in us. Every moment of our lives is quietly connected to the nuclear fires that burned inside stars just like it. The universe is not simply shaped by these stars. In a very real sense, it is made of them. Across the cosmos, the largest star ever found radiates with such overwhelming power that its influence reaches far beyond its own stellar neighborhood. Yet the true scope of its impact becomes fully apparent only when we consider how such a star interacts not merely with surrounding gas and dust, but with the fundamental forces that shape the universe itself. Gravity, magnetism, radiation, and even spacetime are bent and transformed by its presence. To understand how such a star could reshape the cosmos, we must examine how these interactions ripple outward across astronomical distances, triggering changes that persist long after the star itself has vanished. In the regions surrounding a hypermassive star, gravity dictates the earliest form of influence. The star's enormous mass creates a well in spacetime so deep that nearby stars alter their orbits. Planetary systems forming within tens of light years feel gravitational shifts that destabilize nascent orbits, preventing planets from forming or sending them spiraling into interstellar space. Smaller stars that pass too close may have their outer layers stripped away. Gas clouds can become elongated, twisted, or compressed, depending on their trajectories relative to the star's gravitational field. But gravity is only the first step in a chain of cosmic interactions. The next is magnetism. Massive stars generate magnetic fields that dwarf anything found on Earth. These fields extend thousands of times the star's radius, twisting and folding as plasma flows through them. Charged particles caught in these fields are accelerated to incredible speeds. The magnetic lines snap and reconnect in violent flares, releasing more energy in a second than humanity has produced in its entire history. These flares can alter the behavior of nearby stellar winds and even disrupt the magnetic fields of smaller neighboring stars. Such magnetic violence is not merely a localized phenomenon. It contributes to the shaping of entire nebulae. Clouds of plasma respond to magnetic pressure as they are pushed into arcs, filaments, and shock fronts. Over millions of years, these interactions change the structure of star-forming regions, influencing where new stars emerge and how gas flows through interstellar space. Yet even magnetic fields pale compared to radiation, the most dramatic tool in a giant star's cosmic arsenal. Radiation pressure near the star's surface is so intense that atoms are ripped apart. Molecules cannot form. Dust grains evaporate instantly. But farther out, radiation becomes a sculptor rather than a destroyer. It pushes dust into waves, compressing it into ridges that glow with infrared light. These ridges form some of the most iconic structures ever captured by telescopes. Towering walls of gas, sinuous tendrils, and hollow caverns that stretch across light years. The star's ultraviolet radiation ionizes hydrogen, creating vast bubbles of glowing plasma. These bubbles expand through the galaxy like ripples on a cosmic pond, sweeping up material into dense shells. As the shells collide with colder clouds, shock fronts ignite bursts of star formation. Entire clusters may owe their existence to a single hypermassive star born millions of years earlier. This chain reaction of creation is one of the most profound effects giant stars exert on the universe. Without them, galaxies would evolve too slowly, gas clouds would stagnate, star formation would sputter and halt. By triggering waves of collapse and compression, these stars keep galaxies alive, vibrant, and active. But the cosmic feedback loop does not end with star formation. It extends into galactic dynamics. The collective influence of massive stars, winds, shock waves, supernovae, and black hole formation determines how matter circulates through the galaxy. Hot bubbles rise from the disk into the galactic halo. Cold clouds fall back toward the disk. This vertical circulation mixes chemical elements, distributes star-forming material, and maintains the dynamic balance needed for galaxies to continue evolving. A single hypermassive star contributes disproportionately to this cycle. Its winds carve superbubbles that can break through the galaxy's disk. Its supernova can send shockwaves thousands of light years into the halo. If it forms a black hole that later powers jets, these jets can extend even farther, piercing the galactic halo and depositing energy along their paths. In this way, the largest stars feed energy into the galaxy on scales more vast than any ordinary star can achieve. But beyond these large-scale effects lies a deeper truth. The largest stars influence not only the matter in the universe, but also the structure of spacetime itself. Spacetime, though often imagined as a passive backdrop, bends and warps according to the mass within it. A hypermassive star pushes spacetime into a curvature so steep that the flow of time slows measurably within its gravitational influence. If a planet were to orbit such a star at a safe distance, a clock on that planet would tick slower than one far away. Though these differences are small, they accumulate over long periods, altering the timing of stellar events or the synchronization of binary systems. The star's gravitational sway also alters the trajectories of passing objects. Rogue planets drifting through the galaxy may be captured by the star's gravity or hurled away on new trajectories, acquiring speeds that send them into intergalactic space. Small black holes passing nearby may have their paths redirected, eventually setting up collisions that would never have occurred otherwise. These subtle influences ripple outward, creating a chain of cause and effect that spreads across millions of years. Even after the star collapses into a black hole, these effects remain. The new black hole becomes a gravitational anchor for its region of the galaxy, influencing the orbits of stars long after its own mass has stopped changing. If the black hole acquires a companion star, it becomes even more influential. The accretion disk that forms around it emits X-rays and gamma rays detectable across vast distances. These emissions heat the surrounding medium and alter the ionization balance of interstellar gas. In some cases, black holes formed from massive stars may drift toward the galactic center. As they merge with the central supermassive black hole, they contribute mass, angular momentum, and energy. These mergers shape the black hole's growth, influencing the strength of its jets, the dynamics of its accretion disk, and the behavior of material in the innermost regions of the galaxy. Thus, the collapse of a single hypermassive star may alter the evolution of the entire galaxy over billions of years. But even such sweeping influence ultimately points to an even grander role these stars play. They are the universe's primary engines of chemical evolution. Chemical evolution is the process by which the universe becomes richer and more diverse over time. In the beginning, only hydrogen and helium existed. Everything else, the carbon in every living cell, the oxygen in water, the silicon in rocks, the iron in blood, had to be forged in stars. Smaller stars contribute, but only the most massive stars generate the extreme temperatures and pressures needed to create certain elements. The heaviest elements, such as gold, platinum, thorium, and uranium, require environments so extreme that only the deaths of hypermassive stars or neutron star collisions can forge them. These elements are rare not only because they require extraordinary conditions to form, but also because the stars capable of producing them are so few. When such a star explodes, it produces rare isotopes that seed the galaxy with the ingredients needed for complex chemistry. Planets formed in enriched regions can contain radionuclides that influence geological heating, plate tectonics, and magnetic fields. These processes shape the conditions for life to emerge and evolve. On cosmic scales, the presence of heavy elements influences the formation of entire galaxies. Gas enriched with metals cools differently, forming stars at different rates. Galaxies that underwent bursts of early massive star formation develop distinct structures compared to those with slow, steady enrichment. Thus, the largest stars do not simply produce elements, they dictate the pace and pattern of cosmic evolution. But there is one more level of influence, one that reaches beyond any individual galaxy. Across the universe, the distribution of matter into filaments, clusters, and voids is influenced by the amount of energy injected into the intergalactic medium. Hypernovae from massive stars can heat intergalactic gas, preventing it from collapsing into small galaxies. This process may help explain why the universe contains fewer dwarf galaxies than expected. Instead of forming stars, some regions are kept hot and diffuse by the accumulated energy of billions of ancient stellar explosions. A hypermassive star, with its immense energy output, amplifies this effect. Its radiation and shock waves can blow holes in the interstellar medium that eventually become part of larger cosmic voids. Its heavy element ejecta enrich intergalactic gas, altering the behavior of matter as it flows into cosmic filaments. Even on the scale of the cosmic web, the largest stars may leave fingerprints that persist for billions of years. Yet amid all this grand cosmic architecture, there remains an intimate truth at the heart of it all. The story of a hypermassive star is ultimately the story of transformation. Matter transforms into light. Light transforms into motion. Motion transforms into gravity waves. Gravity waves ripple across the universe, influencing matter far removed from their origin. Over billions of years, a single hypermassive star contributes to the evolution of galaxies, the structure of spacetime, the chemistry of planets, and the emergence of life. Its influence spreads across scales so vast that human language strains to contain them. Its light fades, its atoms scatter, its core collapses, but its effects endure. The universe remembers. The largest star ever found exerts its influence not only outward, across vast stretches of interstellar space, but also inward, into the deepest questions about how the universe behaves, evolves, and ultimately ends. To grasp the full implications of its power, we must follow its effects across cosmic timescales far longer than the star's own existence. Because while such a giant lives only a few million years, its legacy shapes billions of years of cosmic history. It touches everything from the birth of galaxies to the formation of planets, the rise of biological complexity, and even the subtle patterns of the universe's long-term evolution. A single star becomes a thread in a much larger tapestry, one woven not from light, but from transformation itself. Massive stars do not simply burn, they influence. Their radiation shapes how gas cools and collapses. Their winds stir turbulence across light years, and their deaths inject energy and matter into regions far beyond their birthplaces. In the case of the largest star ever discovered, this influence is magnified to an extreme that pushes cosmic feedback to its limits. The energy it emits in its lifetime is so vast that if it were somehow focused into a single beam, it could vaporize a planet across half the galaxy. But the actual effect of such energy spread out over millions of years and across an immense volume of space, is more subtle and more far-reaching. Every star-forming region undergoes cycles of collapse and destruction. Gas clouds collapse under gravity, fragment, ignite new stars, and then are torn apart by radiation and winds from those stars. Hypermassive stars act as accelerants in this process. When one of these colossal giants forms, it speeds up the evolution of its entire region of the galaxy, compressing millions of years of slow transformation into a brief cosmic moment. Instead of forming stars gradually, entire clusters ignite almost simultaneously, triggered by shock waves driven outward by the giant's radiation. This phenomenon produces bursts of star formation, periods where a galaxy rapidly births tens or hundreds of thousands of new stars. Over time, such bursts shape the morphology of galaxies. Spiral arms grow more defined, central bulges accrue stars faster, tidal interactions between galaxies become more violent, and as galaxies evolve, so too does the large-scale structure of the universe. Thus, the largest stars are not mere spectators in cosmic evolution, they are catalysts. But beyond influencing star formation, hypermassive stars also shape the distribution of heavy elements, which in turn determines how planets form. Heavy elements, what astronomers call metals, even though the term includes everything from carbon to iron, are critical for planet formation. Rocky planets require silicon, iron, magnesium, and oxygen. Gas giants require carbon and nitrogen to form their thick atmospheres. Water requires oxygen and hydrogen in the right proportions. Organic chemistry requires carbon chains, nitrogen rings, and phosphorus bonds. These complex elements are forged only in the cores and explosions of large stars. A hypermassive star contributes far more heavy element material than smaller stars, enriching surrounding clouds with levels of complexity that transform them into fertile grounds for the next generation of planets. The more massive the star, the broader its enrichment sphere becomes. A typical massive star enriches tens of light years. A hypermassive star can enrich hundreds. This matters profoundly. The availability of heavy elements determines whether a galaxy can form Earth-like planets at all. Early in cosmic history, the first galaxies contained almost no metals, meaning that planet formation was limited to gas giants with no solid surfaces. Only after several generations of massive star formation did enough heavy elements accumulate to create rocky worlds. And among those massive stars, the largest ones contributed disproportionately. One of them could seed enough material for thousands of Earths. It could enrich an entire region of the galaxy to the point where complex chemistry became possible. Without the contributions of these giants, the universe would remain a simpler and far less interesting place. But while heavy elements influence planet formation, the radiation environments created by hypermassive stars influence the survival of those planets. Regions near such stars are hostile in the extreme. Ultraviolet radiation sterilizes surfaces, X-rays strip away atmospheres, and winds can erode magnetic fields. Yet in some regions farther away, perhaps tens of light years, the influx of radiation can drive chemical reactions in planetary atmospheres, triggering the formation of complex organic molecules. Research into the prebiotic chemistry of early Earth suggests that energetic radiation played a key role in forming the building blocks of life. This raises a profound possibility. Hypermassive stars may not only help create planets, they may help create the ingredients for life on those planets. Though deadly up close, their radiation might catalyze the earliest steps in biology across entire regions of the galaxy. And when these stars die, they leave behind environments rich with the raw materials of life. Their supernova explosions scatter iron, oxygen, carbon, nickel, gold, copper, and phosphorus into space. These materials drift, settle, condense, and eventually become part of planets and moons. Over billions of years, this cycle repeats. Giant stars burn quickly and violently, but leave behind the essential ingredients for advanced chemistry. This interplay of destruction and creation extends to one of the greatest mysteries in astronomy, the formation of supermassive black holes. Observations of the early universe show that the first galaxies contained black holes millions of times more massive than the Sun, even when the universe was only a few 100 million years old. How could such enormous structures form so quickly? One leading hypothesis is that hypermassive stars, much larger than anything found today, collapse directly into black holes weighing thousands or tens of thousands of solar masses. These primordial giants, born in the densely packed gas of the early universe, may have lived fast and died young, collapsing into massive black hole seeds. Over hundreds of millions of years, these seeds consumed material, merged with other black holes, and eventually became the supermassive black holes that anchor modern galaxies. If this hypothesis is correct, then the universe as we know it owes its structure to the earliest hypermassive stars. The beautiful spiral arms of galaxies, the elegant orbits of stars, the gravitational stability of galactic cores, all may trace their origins to the deaths of cosmic giants, whose lifetimes were shorter than the blink of an eye in cosmic terms. These giants also provide insight into the fate of the universe. On large scales, galaxies cluster along massive filaments separated by vast cosmic voids. The shape of this structure is determined not only by dark matter and cosmic expansion, but also by astrophysical processes that heat, cool, and redistribute gas. Hypernovae from massive stars can heat intergalactic gas to temperatures so high that it remains diffuse, unable to collapse into new galaxies. Their shock waves push matter outward, carving channels that later become cosmic voids. Thus, the larger stars influence not only local star-forming regions, but also the formation of large-scale cosmic structure. By injecting enormous amounts of energy into the intergalactic medium, they help determine how matter flows across the cosmic web. Over billions of years, this cumulative effect contributes to the architecture of the universe. These interactions raise another profound question. Could hypermassive stars influence the expansion of the universe itself? While they do not directly affect cosmic expansion in any measurable way, the energy they inject into intergalactic space influences how gas cools, how galaxies grow, and how mass distributes itself across cosmic scales. These processes indirectly affect the measurements astronomers use to study cosmic expansion. The brightness of supernovae, the distribution of galaxies, and the behavior of intergalactic gas all depend, in part, on the influence of massive stars. In this sense, hypermassive stars are woven into the very fabric of cosmology. They shape the universe's evolution and leave imprints that astronomers must account for when measuring its expansion, age, and fate. But their influence reaches into another domain, one much closer to the human scale. The elements forged in such stars eventually become part of planetary systems. On planets like Earth, these elements participate in chemistry that supports life. The iron in human blood, the calcium in bones, the carbon in DNA, all of these once existed inside stars. When we look at the night sky, we are not merely seeing distant suns, we are seeing ancestors. Every form of life owes its existence to stars that died long before the sun was born. The largest stars are the most generous of these ancestors, giving the universe not only light, but complexity. When a person breathes, they inhale oxygen that was born in stars. When they speak, the vibrations in their vocal cords depend on the tensile strength of proteins built around carbon, nitrogen, and hydrogen, atoms forged in stellar furnaces. When they think, electrical impulses in their neurons rely on the flow of ions built from the heavy elements of ancient supernovae. The connection is not poetic, it is literal. Hypermassive stars provided the building blocks of consciousness itself. In this way, the story of the largest star ever found becomes deeply personal. Its ability to reshape the cosmos is not simply an abstract astrophysical concept. It is a reflection of our own origins. It reminds us that the universe is not a static background, but an evolving system in which creation and destruction are inseparable. It shows us that even the most colossal explosions contribute to the quiet emergence of life on planets billions of years later. When such a star dies, its light may fade, but its influence endures in every atom it leaves behind. Its nuclear ashes drift among the stars, waiting to be gathered into new worlds. Its collapse may generate gravitational waves that travel across the universe, subtly altering the positions of distant stars. Its radiation may catalyze the chemistry of life. Its metals may become the foundations of civilizations yet to exist. Its power reshapes the cosmos, not through a single act, but through an unbroken chain of influence that extends across time and space. A star can be massive enough to dominate its region of the galaxy. It can be powerful enough to forge heavy elements and sculpt nebulae. It can be explosive enough to trigger the formation of new stars across hundreds of light years. It can collapse into a black hole that endures for trillions of years. But its greatest power lies in what it leaves behind, the raw materials for planets, for life, for consciousness, and for the continuing evolution of the universe. A star burns and dies, but the universe it helps to build continues. The largest star ever found marks the boundary between what the universe allows and what it resists. Its power pushes astrophysics to its limits, testing how matter behaves under the most extreme pressures. But understanding its full impact requires going even further, past the scales of stars, galaxies, and clusters, into the deep fabric of cosmology itself. When a star becomes that large, its consequences ripple outward in ways that cannot be contained by the region around it. Its radiation, winds, death, and remnants become woven into the ongoing evolution of the universe. Each action expands into an effect that transforms far more than its immediate neighborhood. To fully account for the influence of such a star, we need to follow its legacy, not only across space, but across time. A hypermassive star may only live a few million years, but its effects last billions. In many ways, its story is only beginning at the moment of its death. Once the final light of its surface fades, the universe continues to carry its imprint through shockwaves, enriched gas clouds, gravitational perturbations, and even the formation of exotic objects that far outlive the star itself. It becomes a permanent fixture in cosmic history, long after its existence becomes impossible to detect directly. The transition from life to death for a hypermassive star is among the most violent events in nature. Giant stars cannot end quietly. Their cores collapse under their own gravity, triggering nuclear processes that release more energy in a fraction of a second than the sun will produce over its entire lifespan. The explosion tears apart the outer layers of the star, hurling them into space at thousands of kilometers per second. The shock front from such an explosion becomes a cosmic sledgehammer, reshaping everything it touches. These shock fronts sweep through space, compressing gas clouds into new densities. Molecular hydrogen that once drifted lazily in interstellar space becomes squeezed into dense filaments capable of forming new stars. In some regions, the shock waves shred clouds apart entirely, dispersing their material and delaying star formation for millions of years. Thus, the death of a hypermassive star becomes a kind of cosmic gardener, sometimes planting new seeds, sometimes clearing the field. As these shock waves travel outward, they carry with them heavy elements crafted in the star's core. This enrichment process fundamentally changes the chemistry of entire regions of the galaxy. Before the explosion, the space surrounding the star might contain little more than hydrogen and helium. After it, the same region becomes infused with carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements essential for complex chemistry. These elements eventually cool, condense, and become part of the next generation of planets. Planets that form in the aftermath of such an explosion inherit more than chemical diversity. They inherit complexity. The abundance of heavy elements influences the size and composition of rocky planets, the depth of their atmospheres, and their potential for magnetic fields. Magnetic fields are particularly crucial, as they protect planetary atmospheres from being stripped away by stellar winds. Without magnetic shielding, a planet cannot maintain stable surface conditions long enough for life to emerge. The material left behind by a hypermassive star often becomes the foundation for planetary systems vastly different from our own. They may contain more iron, producing planets with denser cores. They may contain more carbon, leading to exotic carbon-rich worlds with surfaces of graphite or diamond. They may contain more oxygen, enabling thick atmospheres rich in water vapor. Or they may be seeded with elements like phosphorus, essential for the formation of DNA-like molecules. The diversity of planets in the galaxy owes much to the diversity of stars that existed before them, and no stars diversify the universe more than the largest ones. But the most dramatic consequence of such a star's death is not the explosion itself, it is what forms afterward. For the largest stars, the core collapse process is so intense that it does not leave behind a neutron star. Instead, the core becomes a black hole, often dozens or even hundreds of times the mass of the Sun. These black holes do not remain passive. They feed on the material left behind by the explosion, generating powerful jets of radiation that can pierce through star-forming clouds and ionize gas across hundreds of light years. Sometimes, the collapse of a hypermassive star triggers a long-duration gamma-ray burst, one of the brightest events in the universe. A single gamma-ray burst can release more energy in 10 seconds than the Sun will emit in 10 billion years. These events can sterilize entire regions of satellite galaxies if they occur close enough. They are rare, but the largest stars push the likelihood upward, making them critical players in the evolution of galaxies. Such bursts can also influence the evolution of life. If a gamma-ray burst were to occur within a few thousand light-years of Earth, it could strip away part of the ozone layer, exposing the surface to lethal ultraviolet radiation. Over geological timescales, some mass extinctions may have been caused by distant gamma-ray events. A single hypermassive star dying in the wrong place at the wrong time could reshape the biological trajectory of an entire planet. This raises profound questions about how life survives and evolves in a universe filled with cosmic hazards. While hypermassive stars enrich galaxies with the building blocks of life, they can also endanger that life with their explosive deaths. This duality makes their role in cosmic evolution extraordinarily complex. They are creators and destroyers, architects of possibility and agents of extinction. Their influence echoes across time, shaping both the rise and fall of biological complexity. Yet the influence of a hypermassive star extends even further. Its collapse into a black hole becomes an anchor point in the gravitational tapestry of the galaxy. Black holes alter the orbits of nearby stars, perturb stellar clusters, and sometimes merge with other black holes. When black holes merge, they release gravitational waves, ripples in spacetime that travel across the cosmos at the speed of light. These waves carry information about the star's final state, billions of years after the star itself has vanished. The presence of such black holes also affects galactic evolution. Over billions of years, black holes sink toward the center of their host galaxies due to a process called dynamical friction. As they migrate inward, they merge with other black holes, gradually contributing to the growth of the supermassive black hole at the galaxy's core. Thus, the larger stars may play a role in determining the size, mass, and behavior of the supermassive black holes that anchor galaxies. In this way, hypermassive stars are not merely parts of galaxies. They help shape the very structure of galaxies, influence their rotation, and contribute to the stability of their central regions. They may even play a role in determining whether a galaxy remains a spiral, becomes irregular, or evolves into an elliptical shape over time. And their influence is not limited to regions close to their birth. The radiation from a single hypermassive star can travel across thousands of light years, affecting molecular clouds, altering chemical reactions, and shaping how gas collapses or disperses. Over millions of years, such effects can alter star formation rates across large sections of a galaxy. In extreme cases, they might even contribute to the quenching of star formation, slowing the birth of new stars entirely. This interplay of star formation and star destruction feeds into one of the largest scale questions in cosmology. How does the universe transition from an early chaotic state to the structured cosmic web we see today? The answer involves the actions of many stars, but the largest stars play an outsized role. Their explosions contribute to turbulence in the intergalactic medium. Their radiation shapes the ionization state of cosmic gas. Their heavy elements enable the cooling processes necessary for the next generation of stars and galaxies. Without their influence, galaxies might remain small, diffuse, and chemically simple. With their influence, galaxies grow into massive structured systems with rich chemical diversity. Yet perhaps the most intriguing question remains. Could the power of the largest star ever found reshape the entire cosmos? Not in the sense of determining cosmic expansion or altering the fate of the universe. Those processes operate on scales far larger than any star, but in the sense of influencing the distribution of matter, the emergence of complex chemistry, the formation of black holes, the behavior of galaxies, and the development of life, the answer is undeniably yes. A star can reshape the cosmos by reshaping the stories that unfold within it. Every black hole that forms becomes a permanent fixture. Every heavy element released becomes part of future worlds. Every gravitational wave generated travels outward forever, subtly altering the fabric of spacetime. Every enriched cloud that collapses forms stars with different characteristics than the ones before. Every planet born of those clouds carries the potential for life. Every life form that emerges carries the atoms forged in ancient stars. Every civilization that rises reflects the complex chemistry of those atoms. Thus, the legacy of the largest star ever found is not its light, but the cascade of consequences that continue long after the star is gone. The universe is filled with echoes of dead stars. They whisper in the chemical composition of planets, in the energy states of interstellar gas, in the gravitational waves that ripple through spacetime, and in the patterns of galactic evolution. These echoes define the cosmos as surely as dark matter and dark energy. They are threads that connect past and present, creation and destruction, simplicity and complexity. The largest stars are the loudest of these echoes. They burn with impossible luminosities, explode with unimaginable power, collapse into unfathomable densities, and leave behind remnants that shape billions of years of cosmic history. A star can reshape a planet. It can reshape a stellar nursery. It can reshape a galaxy. And in its own way, through countless indirect effects, it can reshape the universe. The cosmos we see today, rich, structured, and filled with potential, exists because stars once lived, burned, and died. And among them, the greatest giants left the deepest marks. They are gone, but their influence remains everywhere. Thank you for watching. If you enjoyed this video, leave a like and share your thoughts in the comments. Send it to someone who you think would enjoy this topic too. And of course, subscribe and turn on the notification bell so you don't miss the next videos. See you next time.